This video is on the least squares regression line. It is a line that minimizes the sum of the squared errors or residuals. So basically it's used to make predictions based on past observations. So your regression line equation is y hat equal to b sub 1 or b1x plus b naught. So y hat equal to b1x plus b naught, where b1 is going to be r times s sub y over s sub x, and that'll be your slope. And b naught will be y bar minus b1 times x bar, which is your y-intercept. So x bar is the mean of your explanatory variable. S sub x is the standard deviation of your explanatory variable. Y bar is the mean of your response variable. S sub y is the standard deviation of your response variable. Here, this first example, find the least squares regression line for all of the given information. So they give you the correlation coefficient, the mean of your explanatory variable, standard deviation of explanatory variable, mean of your response variable, and standard deviation of your response variable. Then all you would do is plug in the values accordingly, according to the relationship. So B1 is R times S sub Y over S sub X. Now, if they don't give you these things, then you have to find them according to the data set that you have. So R is negative 0.946 times 5.612486 over 2.44949. So those are the values that they gave us. When you multiply those out, you get negative 2.1676 as B1. B naught is going to be Y bar minus B1 times X bar. So that's 10 times negative 10 minus, negative 2.1676 times 4. And that'll be 18.6704. So don't forget you have to find B1 first before you find B naught, because B1 is a part of the formula for B naught, or part of the relationship that helps you to calculate what B naught is. Once you found those two pieces, then you go ahead and plug them into your regression line calculator. Y hat equal to B1x plus B naught. So that'd be y hat equal to negative 2.1676x plus 18.6704. So that will be your regression line equation. So we will use this in the next one, or use this type of equation in the next one for the application. And you'll see how that will occur. Let's look at the next example. So here, we're going back to the club head speed, and the distance is the same, 8 observations. It says use the chart to find the least squares regression line. So once again, same type of situation scenario. This book does not focus on the calculation of the regression line, but you need to find an application website or calculator that can find it for you. So in the previous example, if you look at what we had these pieces that they gave us. And so we didn't have to necessarily go to a website to calculate these things. They gave us these things. So we went ahead and put it in the formula and calculated with a regular calculator. In this case, they gave us the data chart for the observations. So what we can do is go to a website, put in these data values, or regression line calculator website, put in these data values and get this equation right here. So make sure you have something reliable that can do that for you. If not, feel free to email me and I can give you some suggestions. So we take these data values, put them in the regression line calculator, and it gave us this equation right here. Y hat equal to 3.1661x minus 55.7966. So the next one says predict the distance of a golf ball. Distance a golf ball will travel when hit with the club head speed of 103 miles per hour. So what you would do is take the 103 and plug it into your equation for x. So remember, that's what the equation is for, the regression line calculator is for, to predict values based on past observations. So we'll take the 103, plug it in according to this equation. The predicted distance that a ball would travel if hit at 103 miles per hour would be 270.3 yards. So y hat represents your predicted y, and it would be 270.3 yards. Last part of this example, determine the residual for the predicted value. Is the distance in the table above or below, in the table above or below average? among all balls hit with a swing speed of 103 miles per hour. So the residual is going to be y minus y hat. And that means your observed y minus your predicted y. Regular y is just your observed y. Y hat is your predicted y. So our observed y in the chart is 274 yards. When this person swung it at 103, they observed that he hit the ball at a distance of 270 yards. So that's 274 yards, excuse me, 274 yards. So we plug that in, 274 minus the 270.3 that we got from B. That's our predicted. And it gives us a positive 3.7 yards. So since the residual is positive, the table value that was observed above is above at the average. Okay, now if it was negative, that means that the table value observed would be below average. Last thing in this section, the coefficient of determination. It measures the proportion of total variation in the response variable that is explained by the regression line. It's represented by capital R squared. It's simply the correlation coefficient squared. It basically states how reliable the regression line is. It's between 0 and 1 inclusive. If R squared is equal to 0, the regression line has no explanatory variable value. If R squared is equal to 1, then the regression line explains 100% of the variation in the response variable. So, quick example, determine and interpret the coefficient of determination for the club head speed versus the distance. So, we already know the correlation coefficient from the previous example. That's 0.939. Then you find the coefficient of determination by squaring lowercase r. So we square the 0.939, and that will be 0.882. You can also convert that to a percentage by moving the decimal 2 places to the right. That would be 88.2%. So the interpretation of that is 88.2% of the variation in the distance is explained by the regression line. And 11.8% of the variation is explained by other factors. So that means that your regression line is 88.2% reliable. So once again, it's 88.2% reliable, 11.8% unreliable, and is explained by other factors. That means if you were to hit the ball a shorter distance than what is expected, other things could come into play like wind resistance, weather, anything of that nature could come into play that will prevent it from actually doing what the equation would actually predict. So it's 88% reliable. 88% of the time, the equation should be on point when it comes to predicting how far the ball should travel when you hit it at a certain speed. All right, let me know if you have any questions.